imagine waking up tomorrow and the sky is gone. No stars, no sun, no black void, just nothing. Not empty space, but the absence of space itself. No up or down. No before or after. No laws, no particles, no possibility. That was reality 13.8 billion years ago. Then, in less than a trillionth of a second, everything changed. The universe exploded into existence from a point smaller than an atom, and it brought with it every law of physics, every ounce of matter, every galaxy you will ever see. The question is how? How do you get something from absolute nothing? How does a cosmic rulebook write itself? And what if the answer has been sitting inside the equations we already have, waiting for someone to notice the pattern? Because here is the secret physicists rarely say out loud. The Big Bang was not an explosion in space. It was an explosion of space. And the deeper we look, the more it seems like the universe might not be a random accident. It might be code. Not metaphorical code, but literal mathematical structure so precise that if you tweaked one decimal place, stars would never ignite, atoms would never form, and you would not exist to hear this. Today we are going to crack that code. We will start at the instant before time, dive through quantum loopholes that allow universes to borrow themselves into existence, decode the strange numbers that seem fine-tuned for life, and end with a possibility that will change how you see the night sky forever. If the universe is a program, who or what wrote it, and can we read the source? Let's start with the biggest misconception. When people picture the Big Bang, they imagine a fireball expanding into a dark room. But there was no room. There was no dark. The Big Bang created the room. Before it, the concept of where did not exist. General relativity tells us that space and time are not a stage where events happen. They are part of the play itself. So asking what came before the Big Bang is like asking what is north of the North Pole. The question breaks down because time itself began at that moment. But that answer has never satisfied anyone. Because if time had a start, what flipped the switch? In the 1980s, physicist Alexander Vilenkin proposed something that sounds like science fiction. He used quantum mechanics, the rules that govern atoms, and applied them to the entire universe. In quantum mechanics, particles can appear from empty space for brief moments. They borrow energy from nothing, exist, and pay it back before the universe notices. Vilenkin asked, what if the universe itself did that? What if the cosmos is a quantum fluctuation writ large, a bubble of spacetime that tunneled into existence from a state of pure nothingness? The math checks out. In quantum cosmology, the total energy of the universe might actually be zero. Add up all the positive energy in matter and light, then subtract the negative energy in gravity's pull, and you get zero. A universe from nothing does not violate conservation laws because the sum total of everything is still nothing. It is the ultimate free lunch. But that just pushes the mystery deeper. Why does the nothing have the potential to fluctuate? Why do the laws of quantum mechanics exist in the first place? To answer that, we need to go smaller. Much smaller. At 10 to the minus 43 seconds after the Big Bang, called the Planck time, our understanding of physics breaks. General relativity says the universe was compressed into an infinitely dense point, a singularity. Quantum mechanics says infinity is not allowed. When two theories contradict, it means we are missing something. The leading candidate to unify them is string theory, or its cousin, loop quantum gravity. Both suggest that at the smallest scale, reality is not made of points. It is made of tiny vibrating strands or loops of space itself. If that is true, then the Big Bang was not the beginning. It was a transition. In loop quantum cosmology, the universe before ours collapsed under gravity, bounced at the Planck density, and rebounded into expansion. The singularity gets replaced by a quantum bridge. This is called the Big Bounce. It means our universe might be one cycle in an endless series, each with different laws, each forgetting the one before. But cycles do not explain why the laws are what they are. For that, we have to look at symmetry. Physics is built on symmetries, patterns that stay the same even when you change your perspective. A snowflake rotated 60 degrees looks identical. The laws of physics are similar. They work the same whether you are in Lagos or on Mars, today or a billion years ago. When a symmetry breaks, new structure appears. It is why water freezes into ice crystals instead of staying a shapeless liquid. In the first fraction of a second, the universe was hot enough that all the fundamental forces were merged into one superforce. As it cooled, that symmetry broke. The superforce split into gravity, the strong nuclear force, the weak force, and electromagnetism. Each break released energy and created particles. The Higgs field switched on and gave particles mass. Without that moment, electrons would be massless, atoms could not form, and the universe would be a soup of light. Here is where it gets strange. The values these fields settled into seem arbitrary, but they are not. The strength of gravity is 10 to the 39 times weaker than electromagnetism. If it were only 10 to the 33 times weaker, stars would burn out in a year. If it were 10 to the 40 times weaker, stars could not form at all. The mass of a neutron is just 0.1% larger than a proton. If it were 1%, all protons would decay into neutrons, and there would be no hydrogen. No hydrogen means no water, no stars, no chemistry. This is the fine-tuning problem. The standard model of particle physics has 26 constants that look like they were dialed in. Change any one of them slightly, and the universe is sterile. Physicists call this the anthropic principle. We observe these values because if they were different, we would not be here to observe anything. But that feels like a non-answer. It is like finding a room where every object is perfectly placed and concluding, of course it is, or I would not be standing in it. There are three main ways to explain fine-tuning. Option 1 is chance. Maybe there are infinite universes, each with different constants, and we live in the one that works. This is the multiverse. Inflation theory, which explains why the universe is so flat and uniform, predicts that space never stopped expanding. Our Big Bang was just one bubble in a frothing sea of bubbles. Each bubble has its own laws. Most are dead. Ours got lucky. Option 2 is necessity. Maybe the constants are not free to vary. Maybe a deeper theory, a final equation, shows that they have to be what they are. We just have not found it yet. Think of a circle. You do not get to choose pi. It is fixed by geometry. Maybe the universe's numbers are fixed by some deeper geometry of reality. Option 3 is design. Not necessarily a bearded figure in the sky, but some kind of selection principle. In John Wheeler's participatory universe, observers are necessary to collapse quantum possibilities into reality. The universe exists because it is observed, and it is observed because it exists. It is a loop. Others suggest that universes might reproduce through black holes. Every black hole births a new universe with slightly mutated laws. Universes that make more black holes, like ours with its stars, get naturally selected. To test these ideas, we need to look at the earliest light. The cosmic microwave background, or CMB, is the afterglow of the Big Bang, released when the universe cooled enough for atoms to form 380,000 years later. It is almost perfectly uniform, with temperature fluctuations of only 1 part in 100,000. Those tiny ripples are the seeds of all galaxies. They were stretched from quantum jitters during inflation. In 2014, the BICEP 2 telescope thought it found swirls in the CMB polarization, the smoking gun of gravitational waves from inflation. The signal turned out to be dust. But the search continues. If we find those primordial waves, it would prove inflation happened and give us energy scales 1 trillion times higher than the Large Hadron Collider. We would be looking at physics from 10 to the minus 32 seconds after the start. Even stranger patterns might be hiding in the CMB. In 2005, physicist Roger Penrose noticed concentric circles in the data. His conformal cyclic cosmology suggests that before the Big Bang, there was another universe, and supermassive black hole collisions in that universe sent gravitational waves into ours. The circles are its last message. Most cosmologists are skeptical, but the data has not been ruled out. The CMB also tells us what the universe is made of. Only 5% is ordinary matter. 27% is dark matter, an invisible mass that holds galaxies together. 68% is dark energy, a mysterious pressure pushing space apart. We have no idea what either one is. Dark matter does not emit light, but we see its gravity. Dark energy was discovered in 1998 when supernovae showed the expansion of the universe is accelerating. Einstein originally put a number called the cosmological constant into his equations to keep the universe static. When Hubble showed the universe expands, Einstein called it his greatest blunder. Then we discovered the expansion is speeding up. The cosmological constant was back. The problem is, quantum field theory predicts it should be 10 to the 120 times larger than what we measure. That is the worst prediction in physics. If dark energy were that strong, space would have blown apart before galaxies formed. The fact that it is tiny but not zero is another fine-tuning. Some think dark energy is not constant. It could be a field called quintessence that evolves. If it decays, the acceleration could stop or reverse, ending in a big crunch. If it grows, it could rip apart galaxies, stars, atoms, and finally spacetime itself in a big rip. We do not know which future is ours because we do not know what dark energy is. Now let's talk about information. In 1974, Stephen Hawking realized black holes are not totally black. They leak radiation and slowly evaporate. But if a black hole destroys information, it breaks quantum mechanics. This is the information paradox. In 2019, physicists found a solution using quantum entanglement. Information is not lost. It is encoded on the black hole's surface and eventually comes out in the radiation. Juan Meldacena took this further with the holographic principle. He showed that a universe with gravity in 5 dimensions can be described exactly by a quantum theory on its 4-dimensional boundary with no gravity. It means our 3D reality might be a projection from a lower dimensional surface. The universe could be a hologram. If so, then spacetime is not fundamental. It emerges from quantum information. That flips the creation question. Instead of asking how matter appeared in space, we ask how space appears from information. Physicist Eric Verland argues that gravity is not a force. It is an entropic effect. When you move objects, you change the information content of the universe, and that creates the illusion of gravity. In this view, the Big Bang is when the information capacity of the universe started increasing. This connects to computation. In the 1960s, Rolf Landauer showed that erasing 1 bit of information produces heat. Information is physical. In 2012, Vopson proposed that information has mass. If true, the universe's total information content would affect its expansion. Some estimates say the universe will create enough information in the next 100 billion years to account for all its missing mass. So what if the universe is a computer? Not a metaphor, but literally processing information. Seth Lloyd calculated that the universe has performed 10 to the 120 operations on 10 to the 90 bits since the Big Bang. That is more than every laptop on Earth. The laws of physics would be the software. Particles would be the memory. Time would be the clock speed. If it is a computer, what is it calculating? Oxford philosopher Nick Bostrom's simulation argument says any civilization that survives long enough will run ancestor simulations. If so, simulated realities would outnumber base realities. Statistically, we are probably in one. Physicist James Gates found error-correcting codes, the kind used in browsers, embedded in the equations of supersymmetry. He did not put them there. They emerged from the math. But simulation theory has a problem. It just pushes the creation question up one level. Who built the simulator? The same problem religion faces. If God created the universe, who created God? The only way out is a loop or a brute fact. Maybe the universe is a self-executing algorithm. In mathematics, some systems are self-contained. The Mandelbrot set exists because of a simple rule, yet it produces infinite complexity with no designer. Lee Smolin's cosmological natural selection says universes reproduce through black holes. Universes with laws that make lots of black holes have more offspring. Over generations, the constants evolve toward values that produce stars, which collapse into black holes. We are not in a designed universe. We are in a fit universe. That still leaves the initial state. Why is there something rather than nothing? Lawrence Krauss argues that nothing is unstable. In quantum field theory, empty space has energy. True nothing, no space, no time, no laws, might be impossible. Nothing would have no properties, no rules preventing something from happening. So something happens by default. The universe exists because nothingness is too restrictive. But here is the final twist. In 2021, physicists used quantum computers to simulate a wormhole. They sent a qubit through and it came out scrambled but recoverable. The experiment hints that spacetime itself might be built from quantum entanglement. Two particles entangled share a connection outside space. If enough particles entangle, they create geometry. Space is not a thing. It is the way information is organized. If that is true, then the Big Bang was not the birth of matter. It was the moment the first entanglement happened. Before that, there was no distance because nothing was connected. The first link created the first interval. From there, a network grew. The universe inflated as entanglement spread. Galaxies formed where entanglement was dense. Voids are where it is sparse. This means the code of the universe is not written in the stars. It is written in the relationships between things. The universe is not made of stuff. It is made of correlations. You are not separate from the cosmos. You are a knot in its network, a pattern of information that became self-aware. So did we crack the code? Not yet. But we have the pieces. The universe seems to come from nothing, but nothing has laws. Those laws look fine-tuned, but maybe they are selected or inevitable. Matter is energy, energy is information, and information might be all there is. The Big Bang was not a beginning. It was a phase change. Space is not a container. It is a computation. The next step is testing it. The James Webb Space Telescope is looking at the first galaxies. If they formed too early, inflation is wrong. The Euclid mission is mapping dark energy. If it changes over time, the cosmological constant is dead. Quantum computers are simulating small universes. If we can create spacetime from qubits, we will know the code is real. And here is the part that keeps physicists awake at night. If the universe is a computation, then in principle it can be hacked. Not by us, not yet, but by whatever runs it. The constants could change. The laws could update. The program could end. Or maybe we are the update. Maybe consciousness is the universe's way of reading its own code. Look up tonight. Every photon hitting your eye is 13.8 billion years old. It was born in the Big Bang and traveled the entire history of the cosmos to reach you. In that moment, the universe is observing itself through you. You are not in the universe. You are the universe, temporarily arranged as a person, trying to figure out how it began. So the final answer to cracking the code might not be an equation. It might be a realization. The universe created observers to ask the question. And by asking, we complete the loop. The code creates us, and we decode it. The beginning and the end are the same event, viewed from different points in the network. And if that is true, then the universe was never created. It is creating, right now, and you are part of the process.